Okay, this is the last video lecture on polynomial functions. You made it. We're going to put it all together. We want to find all the zeros, including the complex ones or the imaginary ones as necessary. So our objective, find the complex zeros of a polynomial function. In other words, solve the polynomial to find all the zeros, real and non-real. Okay, we know a few things that are going to get us started here. We've talked about these, and they're going to come into play in this video lecture. What's a polynomial? So number one, a polynomial function of degree n has n zeros or roots when we include multiplicity and complex numbers. Okay, number two, the rational zeros theorem. If a polynomial function written in standard form has integer coefficients, then any rational zero must be of the form plus or minus p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. Number three, we know the factor theorem. If f of c equals 0, in other words, if c is a 0 or a root, then x minus c is a factor. Okay, let's review. We're going to use the same procedure to find all the zeros that we used to find the real zeros. So I didn't copy that over. I'm just going to go back and take a look at that sheet to review this with you. But instead here, we're going to find all the zeros. Okay, number one, use the polynomial's degree to determine the number of roots, the total number, because now we're beyond just the reals. Number two, if the polygon has integer coefficients, use the rational zeros theorem to identify those rational numbers that can potentially be zeros. Number three, let's graph it and find the best choice of potential rational zeros that we're going to test. Number four, use the factor theorem to determine if a potential rational zero is indeed a zero. If it is, we're going to use long division to factor it, and we're going to continue that process as necessary until it's factored. All right, so let's get ourselves started. This might take a page and a half of paper. So let me get another piece of paper out here, just a second, in case I need it. All right. So here we go. Let's see here. I'm just going to do one example for this. Okay, so find all zeros. Okay, which means find the complex zeros. We know complex includes the real numbers as well, of the polynomial function. Okay, f of x, and we're going to have a degree 3 polynomial here, 2x cubed plus 3x squared plus 8x minus 5. Okay, so step one, okay, this is a degree 3. So we know we have 3 zeros. And remember, we're including duplicates and we're including including imaginary complex here, okay? But there will be 3 zeros. Okay, step two. Let's determine any potential rational zeros. So P, okay, P is going to be the factors of -5. Okay, and that equals, well, we got plus or minus 1 and plus or minus 5. We only have 2 factors of -5. Q is the factors of the leading coefficient, which is positive 2. And the factors of 2, well, that's pretty simple. Positive or negative 1, positive or negative 2. So our potential rational zeros are equal to plus or minus P over Q, which equals plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 5 over 1, and plus or minus 5 over 2. 1 over 1, 1 over 2, 5 over 1, 5 over 2. We can simplify that to be positive or negative 1, positive or negative 1/2, positive or negative 5, and positive or negative 5/2. Okay, so we have 8 potential rational zeros. Okay, so let's take a look at our graph and see if there are any of these that we can come up with that we can test. So I'm going to come into my graph here. I want to graph this function right above my calculator. I think I've already entered. Let's go to y equals. Sure enough, 2x cubed plus 3x squared plus 8x minus 5 is the function. I'll go to my standard window to start. And here it is. Heck, it almost looks like a straight line. It's got a bit of a curve to it as it goes up, but it certainly is not a lot else going on with this one. But it only crosses the x-axis. There's only one real root. It only crosses the x-axis at one point. Okay, let's zoom in on that point and see what that is. Actually, yeah, we'll zoom in a little bit. I'll go from, I'll go from my window. We'll go from -2 to 2 and graph it. Here it comes in. It looks like it's almost going to be exactly 1/2. So if you want second calc, my zeros, let's do some bounds on that one and see if it's really 1/2. Okay, bounded left and right, take a guess. Indeed, there's a 0 at 0.5, 1/2. And that was one of our potential 8. Here's positive 1/2 right here. Okay, so step 3. From the graph. Okay, 1/2 appears, we know what it is, but we'll say it appears, if I can write appears, to be a rational 0. Let's check it using the factor theorem. That's step 4. Okay, so we're going to put 1/2 into the function. So what is f of 1/2? Well, the function says 2 times, in this case, the input, which is 1/2, is going to be cubed, plus 3 times the input, which is going to be 1/2 squared, plus 8 times the input, again 1/2, minus 5. Well, I've already put that into my calculator. If you'd like to do that, this is 1/8 times 2, plus 3 times 1/4, plus 4 minus 5. Out comes 0, which confirms by the factor theorem that that's actually a 0. Okay, so 1/2 is a 0. Okay, so x minus 1/2 is a factor. Okay, so now it's time to get into our long division, which is probably everybody's favorite thing. Let's see here. So let's do, where's mine? There we go. X minus 1/2 is a factor of this function. Again, back up to the top here. The function is 2x cubed. Okay, 2x cubed plus 3x squared plus 8x minus 5. And let's get started with some long division to find our quotient. Okay, another factor. So this goes in here 2x, is that right? 2x? Yeah, 2x. X goes into 2x cubed, 2x squared times 2x squared times x, 2x cubed. 2x squared times negative 1/2 is negative x squared. Okay, parentheses, subtract. 3 minus a negative is 3 plus, so it's 4x squared. Now bring down the other two terms. X goes into 4x squared, 4x times. Okay, 4x times 4x is, 4x times x is 4x squared. 4x times negative 1/2 is negative 2x, I hope. Parentheses, subtract. 0, 8x minus a negative 2x is 10x minus 5. X goes into 10x 10 times. 10 times x is 10x. 10 times negative 1/2 is negative 5. Subtract, and we come up with a 0, but we knew that because we knew that x minus 1 was a factor, so we knew it went into the polynomial function with no remainder. We just wanted to know this. What is the quotient? Okay, so we got here f of x so far factors as x minus 1/2 times the quotient up here, which is 2x squared plus 4x plus 10. And actually there's a common factor of 2, so we can pull that out and pull the 2 out. 2 times x minus 1/2 times x squared plus 2x plus 5. Okay? So we know that, and I'm going to need more paper, it looks like. Okay, so let's go back. So let's write that again up here. So let's see here. F of x equals, I'm going to copy that over, x minus 1/2 times x squared plus 2x plus 5. Now, I know that this is not factorable. So we need to use the quadratic formula or completing the square to come up with what these factors are. So I'll tell you what, I'll use the quadratic formula. So let's see here. X is equal to negative b, so negative 2 plus or minus the square root. B squared is 2 squared. Minus 4 times a is 1, times c is 5. All of that over 2 times a, which is 1. So there's my quadratic formula. This is equal to negative 2 plus or minus the square root. Well, the determinant down here is negative 16 over 2, which is equal to negative 2 plus or minus 4i over 2, which means I have two factors. And of course, because remember, your complex factors come in pairs, conjugate pairs. Negative 1 plus 2i and negative 1 minus 2i. Okay, so find the zeros, our factored form, f of x, our final factored form into all linear factors, is going to be 2 times x minus 1/2 times x minus negative 1 plus 2i times x minus this factor, negative 1 minus 2i. And there you have it. Okay, that's the total factored form, and we want to find the complex zeros. Equal, we got 1/2. We've got negative 1 plus 2i, and -1 minus 2i. So because these two, are complex zeros or complex roots, the graph only crosses the x-axis once. If we go back to the graph, you can see that, oops, I'm gonna zoom out, zoom standard again, and you can see that there's your graph. It's relatively simple, and it only crosses the x at one place at +1/2. So there you have it. We put it all together, how to come up with all the zeros of a polynomial function. Congratulations.